All right. So again, the long-term plan, I'm just going to, for the recording, I just want to mention, we're going to do chapter 5, or a good portion of well, not a good portion of chapter 5, but we'll make some distance in it. A lot of vocabulary in the first section, so we'll be going over that. Then we have, we'll do a review on Thursday, and then the next week on Tuesday, I'll open up the test. Chapter 5 are getting what's called polynomials. And these are things you might kind of wonder, when do we actually deal with polynomials? And so what I'm going to do, I'm going to talk about when we actually encounter them. We actually encounter them all the time. In fact, our entire number system, every number we use is really a kind of polynomial. We never showed that's the case, but it actually is. Like 3,333 is a polynomial. 3 is a polynomial. Well, it can be polynomials. I'll explain why. Got to be careful with that 3,333. It is a polynomial, but we're going to express it a little differently. So first off, I'm just going to go over vocabulary that's in the text, because this could come up. So first off, we're going to talk about what exactly is a polynomial. And it's something like this. So we have what are called, linear. And we've encountered linear before. We're going to talk about these. And linear equations are in fact polynomials. And they're typically of this form. We're going to call it P of X. But this is what's called a linear equation. And we have our variable x, our unknown number. And then a1, a sub 0 are constants. So a1x plus a0 equals P of X. So we might say, for example, P of X equals 3x plus 1. So this would be a polynomial. Now I'm really sticking to this P here. I don't have to. I could also write this as f of x equals 3x plus 1. We've seen something like this before. But more recently, we've seen another kind of polynomial. We'll say not another kind, it's a polynomial, but with a different form. So these are the same polynomial. This is the same polynomial. They all are. They're just sort of written a little different. But they're all the same. But to emphasize we're using this word polynomial, we use P of X instead of, say, f of X or Y. But we'll probably see both of these come back. We actually will. But these are all the same type of polynomial. So these are linear equations, which are a kind of polynomial. Another kind of polynomial. So if you're in your notes, you can even put a header above linear equations that says types of polynomials. I'm just going to kind of go through these. We have constant functions. And a constant function would be something like this. So it's just equal to a constant number. So in this case, for example, p of x equals 2. Or we could rewrite it as f of x equals 2. We've seen something like this before. One that we've definitely seen before, another version of the same polynomial, y equals 2. And these are also actually types of linear equations, I should say. These are linear. But they have a slope of 0. So this is just that flat line that you would graph on the Cartesian plane or the rectangular plane. So these kinds of things, and they're linear equations. They're all linear. Particularly, this is a constant function. It's also a linear equation. Another polynomial you've probably seen before. Quadratic equations. Now, these are nonlinear. And we're going to study more of these later. Good. So we're going to study more of these later. And they're of this form. You might have seen them like this. Something like this. This is what we call a quadratic equation. Typically, though, what we usually write as a polynomial, we'll often see this. P of x is going to be a 2x squared plus a 1x plus a 0. So it still has a constant and an x squared, constant and an x squared, constant and an x, constant and an x, constant, constant that are by themselves. So these are all polynomials. And let me give you an example a little more with the quadratic. But we're sort of, what we're doing is we're taking things we've seen before and putting them into this new language. So for example, P of x is 2x squared plus 3x plus 1. So this would be a quadratic polynomial. So in general, what we have is this. I'm going to use the definition from the text. I modified it a little bit different from what's in the book, just to allow for the constant function being a polynomial. But polynomials can be a sum of terms or a single term containing variables with whole number exponents or containing no variables at all. So again, we solve, for example, with no variables at all. What would that look like? Well, again, that's that p of x equals 2. That is a polynomial. It's a very simple one, but it's only one term, and it has no variables. So that is a polynomial. You can have one without variables, and they're going to be those constant terms. All right. So generically, what does this look like? What you'll usually see when we talk about polynomials generically, and I'm going to have to write this on multiple lines because I don't have room on the board, but you can write it all the way across on your notes if you would like. If you write it a little small, not terribly small, a little small. So what it is you have x to the nth power, x to the n minus 1, x to the n minus 2, x to the n minus 3, and you keep going down till you get x cubed, x squared, x to the first power. And you can say x to the 0, but you gotta be kind of careful with that because if there actually was an x to the 0 and you let x equal 0, you have 0 to the 0. So we can just say there's no x there, just to be consistent. But if you want, you can think of it as like x to the 0. Like, be careful. You don't want to get 0 to the 0. So usually just say constant term. You don't say there's no variable here. And so that's the basic form of a polynomial. Now, sometimes, so I'll give you just some more advanced examples. So let's say we have this. Let's say we have something like this. Now, this is what we call standard form, or the polynomial is written in where the terms, one following the other, is using the decreasing powers of the variable. So terms listed in order of decreasing exponents. So here's the exponent, and it's decreasing. The x to the 4th term, the term with x cubed, the term with x squared, the term with x to the 1, and then a term that has no variable. So to look at this, what a sub 4, so this is what we've got. Here's a sub 0. And we say that's -7. Next term here, this is our first exponent. And this is where a sub 1 would be. So a sub 1 is, well, there's nothing, well, there's something there, there's an invisible 1. So there's 1. Now we go to this next term, this would be the a sub 2, and you kind of notice a pattern here. And you saw this in the generic form of the polynomial. A sub 1, exponent 1. A sub 2, exponent 2. Exponent 4, we have an a sub 4. But we'll keep going. A sub 2 will be 5. A sub 3 is 2. A sub 4 is 3. So a sub 4, the x has an exponent 4. A sub 3, x has an exponent 3, and so on. Now, where this could get a little confusing is if we have a polynomial like this. First off, any questions about that? All right. So let's say we have something like this. What do we do with this? We have 3 terms. So is this a 3 term, a 2 term, and a 0 term? Well, this is how this works. We can think of this as 3x to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared. Oh, we do have an x squared. 2x squared plus 0x plus 1. So we can rewrite it in this form. So now if we ask, what are the constants? A sub 5 is 3. A sub 4 is 0. A sub 3 is 0. A sub 2 is 2. A sub 1 is 0. A sub 0 is 1. We can fill in for missing terms by letting 0 be a coefficient. We can fill in those missing terms. And we're going to use this trick later on when we divide polynomials. That's going to be a very useful trick. It'll be indispensable. So any questions about that? All right. So we have some differences here in classifying polynomials, other than, say, constant functions, linear equations, and then quadratics. We have another way of doing this by the number of terms. I'm sorry. I'm having one of those moments where you have a word you've used and you've seen, and then suddenly, yeah. Oh, excuse me. Did I spell that right? That is spelled right. Ooh. All right, naming polynomials. Sometimes we think about something for maybe not the first time, but the first time in a while. And we realize we've been so used to just doing it, we didn't think about it critically. It's like, yeah, you don't have an E after the F. All right. A little reminder on spelling. So naming polynomials. Now, we've already seen some names again. Constant function, linear function, quadratic. And we're going to do a version of naming these where it's the number of terms. So if P of X has 1 term, it's called a monomial. So 1 term is a monomial. To give you some examples. That would be a monomial. That's a monomial. And that's a monomial. They're just single-term polynomials. If we have two terms, it's a binomial. So, for example, again, we've got two terms. Or we can have this. This is also a binomial, just two terms. And again, another binomial. So two terms give you a binomial. And then finally, three terms. Trinomial. So your quadratic that's actually a trinomial because it has three terms. That would be another trinomial. So let's give you two trinomials this time. So we can label these polynomials by the number of terms that they have. Now, we talked about what we call standard form. And that's when we list the terms of the polynomial in decreasing exponents or decreasing powers of the variable. So first off, let's take a look at a term. So if we have a term, say a to the, I won't use n, let's say a to the m. So this here is what's called the coefficient. And you've probably seen this before, but I'm just going to mention it. That's your coefficient. This is your variable. And then we've seen this before, the exponent. So why get into this now? Well, if you recall standard form, we mentioned that you have the decreasing powers of the variable, or the exponent on the variable is decreasing. There's a certain kind of term we look for, and we'll be dealing with this in the future. In fact, we'll be dealing with it right now, very shortly. But when a polynomial is in standard form, the first term is called lead term. So the first term is called the lead term when this polynomial is in standard form. If it's not in standard form, we'll get the wrong lead term, and we don't want to do that. We'll usually work with polynomials in standard form. We can rearrange them to put them in standard form. When we do division with polynomials, we work with them in standard form. When we do factoring, we also use standard form. We always sort of default to standard form. And then its coefficient is called the lead coefficient. So, questions about that so far? All right, let me give you an example. So let's say we have this as our polynomial. 2x squared plus 6x cubed plus 7 plus 8x. Well, what we're going to do, put it in standard form. And again, we have decreasing powers of the variable, or a decreasing set of exponents. 3, 2, 1, then you can maybe say it's just not there. So this here, this is the lead term. And then here, that there is the lead coefficient. So if we don't put it in standard form and we took the first term, we would get things wrong. We would say this is the lead term and the lead coefficient was 2, but that's not correct. We have to put it in standard form, then we can single those out. Now, what we're going to do next is talk about degree. So the degree is the exponent of the variable of the lead term. So for degree, exponent, lead term. So that means the degree of this polynomial, give you a second to put it in your notes, the degree of this polynomial is 3. So this is a degree 3 or third degree polynomial. Questions about that? So there's one last thing with degree I want to mention. And let's say we have a polynomial like this. Let's see here. not a polynomial so much as just something, say, like this. But we could call this a polynomial. This would be of x, y, and z. Now this is a monomial. It contains only one term. Now we won't be dealing with these in this class, but it does come up. I think, let me check your homework here. It should come up with these kinds of things. We don't do too much. We don't graph them or anything. But we do some simplifications. The degree of this term is the sum of the exponents. So when you have a polynomial with multiple variables and there are multiple exponents, the degree will be the sum of those exponents. So 2 plus 3 plus 1, 6. That would be the degree of this monomial. And when you have something like this, let's say something a little more complicated. Here. And let's say we have, we'll use the one in the text. Let's say a polynomial like this. Well, here the degree, there's a 1, and a 1. Better not skip this one. This one has a degree 2 plus 2 plus 4, or 8. This term has a degree of 2. And then when you have a constant term like this, it has a degree of 0. So this is something we're always going to do with constant terms. We say they have a degree of 0. So what's the degree of this polynomial? Well, when we have multiple variables in here, this is what we say. And the degree of this type of polynomial is the largest degree of any of the terms. So what that means is if we take the degree of each term and we compare the degrees, we don't add the degrees, we just compare them. There's a term that will have a largest degree. And that degree is the degree of the polynomial. Questions about that? All right. So that's sort of the anatomy of polynomials. So I mentioned earlier that we actually use these all the time. We're just unaware of it. And there are direct uses for them. A lot of the direct uses are done in calculus. When you get to calculus, you do what are called integrals. And integrals can be very difficult to apply to some functions. What happens is you take a function, take an integral, this is what it looks like, the symbol for an integral, and we might apply it to a function like this. We could apply it to a polynomial. The integral is a second part, there's a beginning part, there's an ending part. And then what you do in calculus is you're going to memorize some formulas that tell you what you should do with each of these terms. And these are formulas that are particular to the integral. Now, some functions, there's a lot of functions out there. There's polynomials, there are trig functions, there are logarithmic functions. Some functions can be very difficult to use calculus on. So instead of using calculus on those functions, we use them on a Taylor series representation. In other words, if we work with a very small portion of the x-axis, because again, we could graph this on the Cartesian plane. We work with a narrow part of the x-axis and we ask what's the integral of some function when we're over this narrow part of the x-axis. We can replace the function with a polynomial that approximates it pretty well. And when we do that, we can then apply calculus. So you do use this in calculus. There's a technique for using polynomials to solve a system of equations like we did in section 3.2. And we can do those kinds of things using polynomials, very complicated systems of equations. But where you see these in everyday life, I mentioned 3,333. Now, first, I do need to mention one thing. And we've seen this before. For evaluating, we want to have this under our hat. Now, we've seen this a little bit before. We've worked with, say, f of x. So if we have p of x, let's say a p of x like this. Well, to evaluate a polynomial, let's say we want to know the value of the polynomial at x equals 2. And I promise this will have some bearing on why 3,333 could be a polynomial. So the value of p of x at x equals 2. Well, the way we express that, we replace x with 2 everywhere. And then we do computations following PEMDAS. So we better take care of our exponents first. Well, there's parentheses, but these are just numbers in parentheses. There's no operations. So we can just go next to the exponents. Exponents are gone. We do multiplication and division. So knowing PEMDAS, especially for subtraction and addition, is going to be helpful for polynomials. We do subtraction and addition going from left to right. 24 minus 4 is 20. 20 plus 2, 22, and then 22 plus 5, 27. So that's how we evaluate a polynomial. We just substitute or replace x with the number we want to find the value of the polynomial at. And then we follow our PEMDAS, do our exponents first, then do any multiplications we might have to do, then do our subtraction and addition or addition and subtraction, going left to right. So now we get to figure out this whole business with 3,333. Ooh, that's the one that's not there. So let's say we have this. $3,333. We can break this down into 3,000 plus 300 plus 30 plus 30. This is what's called standard form of a number. Now we can break it even further. 3 times 1,000 plus 3 times 100 plus 3 times 10 plus 3. I use that term standard form, and we use that for polynomials. There's a good reason why. It turns out that 1,000 is 10 cubed. 100 is 10 squared. 10 is, well, just 10 to the first. And then we have 3. So we're getting something kind of familiar. We would say that we have a sort of a standard form where we have decreasing exponents. And instead of x, we have tens. So we could write this number like this. $3,333 is this polynomial when we let x equal 10. And we can do this with all of our numbers. And we have to make one commitment. X has to be equal to 10 and nothing else. It can only be equal to 10. And this is what we mean by a base 10 number system. So we can use polynomials to sort of see our number system at work. So any questions about that? All right. So let's get into adding and subtracting polynomials, and we'll finish with the lead coefficient test. We'll stick with the arithmetic, and then we'll step into some of the graphing, and then we'll talk about the arithmetic again next time. So we have these polynomials. So let's say we have this. Say we have something like this. We have these two polynomials. So let's say we want to add them together. So we take p of x plus q of x. Well, we start out with p of x plus q of x. I mean, that's what they told us to do. So here we are. Now we replace P of x with its alternative identity, or you could say its secret identity. And then replace Q of x with its secret identity, sort of Batman and Robin. So what do we get? So there's P of x plus, and now we bring in Q of x. Well, again, with parentheses, we can drop them unless we need to distribute something. So if we need to distribute something, we can only drop the parentheses if we do our distribution. But in this case, there's nothing to distribute, and we can't combine any terms first in these parentheses, so we're actually free just to get rid of them. So at this point, what we do, combine like terms. So we have a 3x squared minus an 8x squared. We have a plus 2x. So you have a plus 7x to the fourth. And then we have a 1 and a 7. So really the only terms to combine here are the x squared terms and then the constant terms. So 3 subtract 8. Subtracting a bigger number from a smaller number, that's always going to be negative. So 3 minus 8 would be negative 5. Then 1 plus 7 is 8. So finally, so technically we're done. But what we're going to do with these is we're going to put them in standard form. So that means the term with the highest, the biggest exponent on its variable, it's going to go first. Then we list everything in terms of decreasing exponents. So x to the 2, x to the 1, and then the term where there's no exponent or any variables, period. And that's going to be our answer. So that's how we add polynomials. Now what about subtracting? Let me pull a good one from the book here. So let's say we have this. Get a homework problem. So let's say we have this. We're going to subtract these two polynomials. Well, the first thing we're going to want to do is we want to get rid of these parentheses. So before we didn't have anything in front of the parentheses to distribute, so we could just drop them. So we could drop these right here. But this one we've got a minus sign, so we better distribute what's on the outside. or multiplied or attached to the outside. In this case, we have a minus sign that's attached. So this will go to every term. So we drop these exponents, I'm sorry, parentheses. And so the negative makes this negative, negative and negative is positive, negative and negative is positive, negative and positive is negative. And now we combine like terms. So we have the 17x cubed minus 5x cubed. Now we have a minus x squared and then a plus 9x squared plus 4x plus 8x, a minus 3 and a minus 11. So combining these terms, 17 minus 5, 12x cubed, minus 5 and a positive 9 is a plus 4. 4 plus 8 is 12. And minus 3 subtract 11, so it's minus 3 degrees, and it got 11 degrees colder, minus 14. And so that would be our answer. Questions about that? So this is 5.1. The last thing I want to mention, the 5.1, and this seems a little random to get into this now, but we're going to take a break from the arithmetic. And we're going to get into what are called end behaviors. So the idea of end behavior is this. When you graph a polynomial, if you have a graphing calculator and you just come up with some sort of randomly inspired polynomials and just graph them and see what they look like, depending on how big the degree of your polynomial is and how many terms there are, you could have all kinds of crazy stuff. But ultimately, at the far ends of the polynomial, you'll get to where the polynomial just decreases or just increases. It stops going up and down. It has a constant decrease, well, not constant, but a consistent decrease and a consistent increase. Constant increase and decrease we use to describe lines. So because it could be curving down or curving up, I won't say constant because that means it's a line. I'm going to say consistent, that it's always still dropping, but it's going to be doing it maybe in an arc or rising in an arc. But it's always rising consistently or always decreasing consistently on the ends. So it's like this. At the infinities, the graph of a polynomial either increases or decreases consistently. It'll increase or decrease consistently. So what would this look like? Well, for example, we could graph a polynomial on a graphing calculator. Let's see, we might get something like this. So if we look in the middle of the graph, in the middle, the behavior is up and down. So the graph is moving up and down in the middle. But on the ends, it's going to be consistent. So this is what we mean by end behavior. In the middle, this could be doing all kinds of things. But on the ends, it'll be consistently upward. So when we're concerned with end behavior, we're not really, I'm going too fast, let me know. When it comes to end behavior, we're not interested in what's going on in the middle. We just want to know what's going on in the ends. So we don't know what's going on in the middle, and we're not going to be really concerned. But we're definitely going to be interested on what's going on in the ends. I'm not going to be interested in the middle. So now what we want to try to do is predict the end behavior. Now, one way we could do this is we could graph this on a graphing calculator or graph it using test points and graph enough of them until we see what this thing seems to be doing. But there's a more surefire way of doing that, and an easier way. It's called the lead coefficient test. And it works like this. when you identify the lead coefficient, it tells you what the end behavior is for the lead term. I should be careful. Is it lead? They call it the leading coefficient test, but it's really going to be the lead term. So we're going to do a little, how does one say, not exact, it's sort of like fortune telling. You can think of the lead term as the palm of this polynomial's hand. We're going to look at certain properties and try to guess its future or guess what it does at the extremes of its existence, whether it's on the negative side or the positive sides of the x-axis. So what is it that we're looking for? Well, let's say we have a lead term. Well, it depends, first off, if n is odd or even. So for n is odd or n is even, we're going to get certain kinds of end behavior. So we're going to keep an eye out for that. Is n odd or is n even? Finally, is a to the n positive or negative? So the two things we're going to consider: even or odd, positive or negative. Now this will always be positive. This here could be even or odd, that doesn't matter. It's only if it's positive or negative. So how does this break down? Specifically, this is what you're going to get. A little question mark in here. Another question mark. So what we have is we have some Cartesian planes, and we actually have some polynomials that we graph. Now we've only graphed the middle parts, but they're hidden behind these boxes. They're doing all kinds of crazy up and down things. But we're interested in what's going to be the end behavior coming out of each of these boxes. So there's a polynomial here doing its up and down thing. So how does it come out at the ends? Well, if a to the n is positive and n is odd, whatever's going on in the middle, who knows? But on the negative side, we'll have this. And on the positive side, we'll have that. Positive, negative x-axis, positive x-axis. Now, if a to the n is negative, remember, this is the lead coefficient of the lead term. This is the exponent on the lead term. If a to the n is negative, but the exponent's odd, we're going to see this. It flips around. Now let's suppose n is even. If the exponent is even and the lead coefficient is positive, we'll do some stuff up and down. But at the ends, we'll get something like that. And again, if n is even and the lead coefficient is negative, this will flip. And we'll get something like that. So any questions about that? All right. So just as an example, let's see here. So we're going to use f of x instead of p of x, which is okay. To use y if we wanted to. So let's take a look at this. We've got this polynomial. We want to identify the lead term. Well, first off, it's already in standard position. So that's good. So it's easy to identify the lead term, which will be the first term of the polynomial in standard position, or the term that has the highest degree in this polynomial. So the lead term and then we take a look at this. So a to the n is negative. And then n equals odd. So that means for the end behavior, if you take a look at your chart, look for where n is odd and a to the n is negative, you're going to get something like that. And this will be going up and down and all sorts of things on the inside. So that's the deal with polynomials. Now what we're going to look at next is, a couple minutes, we're going to look at multiplying polynomials. And then we're going to look at undoing this process of multiplication. And we call that process of undoing the multiplication factoring. And we'll be spending some time with factoring. We'll be looking at 5.3, 5.4, 5.5, 5.6. Will all about be factoring. So we'll take that when it comes. So we're going to look at multiplying next. Multiplying is not too bad. There's a distributive way of multiplying when you have polynomials with multiple terms. You have a monomial with polynomial. You distribute the monomial. Polynomial, you actually distribute the polynomial one into the other, and then you distribute each monomial into the distributed polynomial. Woo. And then for binomials, you multiply those together. We have something called FOIL. So we're going to take a look at this, and we'll jump into multiplication fairly easily. And we'll get in the fact, we'll do it in one section. Whether it's easy or not is another story, but we'll cover it in one section. And then for 5.3, 5.4, 5.5, and 5.6, we're going to try to figure out how to undo that multiplication. And that's called factoring. And there's different techniques for doing this. So that's it for today. Again, we're going to look at doing a review on Thursday and then the test on Tuesday. And I'm going to take a look at the schedule, see how we are on pace. If I make any changes, I'll let you know. And other than that, have a wonderful afternoon.
So just double checking, 5.1 and 5.2 aren't due today?